Hello, everyone, and welcome to this latest webinar from Omdia, brought to you by Informatech. My name is Alan Tatara, Senior Event Manager for the Omdia webinar team, and I want to thank everyone for joining us. Today's webinar is Future-Proofing Optical Networks with Next-Gen ROADMs. Our expert panel will explore how flexible next-generation ROADMs can serve to future-proof networks quickly and cost-effectively. Our webinar is co-presented by Omdia and our partners Ciena, Fujitsu Network Communications, and Lumentum. So now let me take this opportunity to introduce our panel. First, leading our discussion is Timothy Monks. Tim is a Senior Principal Analyst in the High-Speed Optics and Optical Network Technologies segment at Omdia. We are also joined by Kent Jordan. Kent is an advisor of portfolio marketing at Ciena. We also have Rob Hughes. Rob is an optical solutions lead at Fujitsu Network Communications. And rounding out our panel, we have Dr. Brian Smith. Brian is part of the CTO office at Lumentum. So welcome to our panel. We are honored to have you with us today. So let me now turn it over to Tim so we can get started. Tim?
Thank you, Alan, and welcome everyone to our webinar on future-proofing networks with next-generation ROADMs. In this webinar, we'll focus on ROADMs and how switching at the wavelength level in various optical networks can be used to maximize network bandwidth, increase network capacity, as well as more efficiently use the very valuable amplified spectrum. We have a lot of material to get through today, and so let's get started and jump into this. In the first part, I'll look at key market trends that are affecting the industry, and then we'll go from there. Okay? So one of the key market trends is looking at revenue and Capex by communication service providers, ICPs, and carrier-neutral providers, the big four segments. Although the carrier-neutral is relatively small, it is growing. But as you can see, revenue for ICPs has grown pretty nicely. It's grown from $770 billion in 2011 to $1.6 trillion in 2019, and the Capex has gone up significantly as well, $33 billion to $116 billion over that same period. With the communication service providers, revenue and Capex have been relatively flat over, the past 8 years. Their combined revenue is just shy of $2 trillion, and combined Capex was around $335 billion. Carrier neutral's revenue is $56 billion, and their Capex is $20 billion. So their capital intensity, which is Capex divided by revenue, is quite high. It's high. ICPs are pretty low. That's around 7%, and the communication service providers' capital intensity is around 18%. One of the interesting things, the ICP, as most people know, has been growing rapidly. It's provided a lot of lift for optical networks over the past 8 years, and is expected to continue to do so. We expect by 2022 that the combination of ICPs and CMPs will be equal to the revenue of the CSPs. But I guess the main point is that for a lot of this segment, Capex and revenue are flat. In general, the segment's growing at about a 4 to 5% increase in revenue and Capex on a CAGR basis. So looking at this, so going back over really the Coherent period, Coherent started in 2010, 2011. What we've seen is the deployed bandwidth, basically, of Coherent modems has been growing exponentially. It's been growing at about 30% per year. In the early days of the Coherent era, from 2010 to 2015, where there was a lot of innovation in this new technology, the costs per gigabit were going down at about 30%. So looking at the red line, this is the cost, this is the actual bandwidth, deployed bandwidth growth. the cost or the spend by the carriers has actually started to increase after 2015. And that's because the cost per gigabit has really started to slow as innovations have become less frequent, and but the deployed bandwidth continues to grow exponentially. So really, equipment-focused savings are becoming more incremental. The bandwidth continues to grow exponentially, and something's got to give. So, what we're looking at is how, in this webinar, how next generation ROADMs can help with this problem and alleviate some of the stress that we're seeing due to the accelerated growth in deployed bandwidth relative to flat or slowly growing revenue and Capex. So bandwidth's growing much faster than revenue and Capex, and we expect this trend to continue. This is the forecast for revenue and Capex over the period from 2020 to 2025. We see a little dip in 2020 due to COVID primarily. Primarily happened in first half over in Asia, or first quarter in Asia, and second quarter in Europe and North America. So I expect a small dip in Capex, not really in revenue, but in Capex this year, but then continued growth of that. But as you can see, most of that growth is coming from the ICPs. We're also moving up into higher data rates. Last year, 600 gig was introduced. This year, 800 gig is being introduced. We've gone up about 8x over the Coherent period in bandwidth or data rates per Coherent modem. Another trend we're seeing is that Coherent modems are being kind of developed by applications. So you're seeing, in the early days it was kind of one size fits all. You can use it for, links that are 80 kilometers, or you can use it for links that are 1,000 kilometers. Now we're seeing more specialization, smaller pluggables for the shorter DCI links, and then these compact modular, as well as the traditional line cards for the regional long haul sub-C links. Okay, in this next section, we're going to go through the problems and challenges facing the industry, and really have a look at what we need to do to or outline these problems and challenges and set up for where we're going to solve those. I will now turn it over to Brian for Lumentum's perspective on the problems and challenges facing our industry.
Thanks very much, Tim. So let's start this off by taking a look at how the data rates have evolved over time, and what happens as we start to push these rates higher. So let's rewind to 2000. We had 10 gigabits per second and a 50 gigahertz channel. And that meant, if you look at the right-hand side, we could achieve a total of about a terabit of capacity in the C-band over a single fiber. Now, we weren't really using much of the 50 gig spectrum there, you can see, so it wasn't very spectrally efficient. So if you look down a bit, you can see that as the interface rates evolved from 10 gig up to 200 gig, every single incremental increase in the data rate results in the same incremental increase in C-band capacity, and you can see that with the times numbers. So 4 times from 10 to 40 gig, 2.5 times from 40 to 100 gig, and so on. Now, over that time, you can see from the diagram that we're making much more efficient use of the fiber. So that was through a combination of higher baud rates, basically using up more of the channel spectrum, and also higher density modulation formats. Now let's fast forward to 2020. So to get 400 gig from 200 gig without reducing reach, we've got to double the baud rate, so going from 32 to 64 gigabaud. Now, this no longer fits in a 50 gigahertz channel, Okay, so the channel bandwidth also needs to increase, so a minimum of 75 gigahertz, as I show there. So the reason is the result of that is that we double the interface rate from 200 to 400 gigs, so 2 times, but we only get a 25% increase in the capacity. That's because we've got less channels in the C-band. So let's look ahead to 800 gig. And if you want the same reach, we have to double the baud rate to 128. We actually get no improvement in the C-band capacity at all. And that's because we also need to double the channel bandwidth to support that higher baud rate. So we might double the interface rate, but we've got half the number of channels in the C-band. So we get no improvement. What this is saying is that we're reaching a limit of how much capacity we can squeeze out of a single fiber. And if that's the case, how do we go about continuing to grow capacity at the scale that was suggested by Tim's market trend data? So the only way to support traffic growth going forward is to increase the total amplified bandwidth. So in cases where there's plenty of deployed fiber, on the left-hand side, one approach is to activate additional fiber pairs per route. So in this way, you get multiple increments of C-band spectrum per direction. The other case is maybe fiber is scarce or the cost of additional fiber is prohibitive. And in that case, combining the C and the L-band over the same fiber is definitely the way to go. That gives you twice the capacity, essentially. Now, both of these strategies that I show here, they're already being deployed today. So Tim mentioned that the traffic was growing, or the capacity was growing about 30% year on year. If you think about deploying C plus L, that gives you about 2.5 years of capacity growth before you need to start adding more fiber pairs. So you could see both of these approaches being deployed simultaneously to support that growth. Now, this is just an architecture view of what's required. So Kent and Rob, they're going to elaborate on how these strategies can be achieved much more effectively and efficiently. And with that, I'll pass over to Kent.
Okay, thank you. So this slide is going to just give a brief overview of some of the different options for ROADM configurations, and it's really just to make sure everyone's familiar with the different options and we're all starting kind of from the same baseline. So starting with the most basic fixed configuration on the left, the fixed option lets you introduce the ability to point-and-click provision an end-to-end light path and remotely configure all the intermediate ROADM sites as pass-through. So you can think of it as basically having an automated patch panel at every intermediate site, but everything at the add-drop node is still going to be fixed from the channel spacing and the channel width to the direction the wavelength actually is going to leave the site. And then next would be a colorless ROADM, and this really just adds the flexibility of being able to support any color on any port. And this is where you start to bring in flexible grid capability, which means now your line system can support next-generation coherent modems and higher baud signals. It allows you to flexibly select the optimal channel width and the optimal channel spacing, but your add-drop is still going to be fixed to a specific direction. That leads us to colorless directionless ROADM, which adds the ability to remotely switch wavelength paths. So your wavelengths that are being added are no longer fixed to a specific direction. A wavelength that's added at a location can be configured to leave that site whichever direction you want, and it can be remotely reconfigured if traffic patterns change. Now, there's still going to be some restrictions on wavelength add drop that could lead to a blocking situation, which basically then leads us to the final most flexible option, colorless, directionless, contentionless, or simply CDC ROADM. This is where you've got full flexibility, no routing restrictions. It's the simplest from an operational perspective. Now you can add wavelength color 1 for the east direction. You can add another instance of wavelength number 1 for the north direction and another instance of wavelength number 1 for the west direction. and there's no blocking at the site. They can add drop on whichever port you want. Essentially, you've got a fully remotely reconfigurable ROADM, and this enables really a cookie cutter type deployment across the network. So next, we'll talk about some of the industry drivers that are really pushing us to integrate new features and new tools into the line system to provide increased scale and automation. So depending on what type of network you have, whether it's a metro or a long haul, whether it's got a large number of sites or a small number, or it's got more point-to-point or any-to-any connectivity, you might be seeing some of these drivers in that network, or maybe you're even seeing all of them. The first two are really related to automation. So today, many networks have more manual processes where you're inputting planned fiber data, or you may have inaccurate or old fiber characterization data where something in the network might have changed, but for whatever reason, it's not reflected in your most recent characterization data. And then you take that data and you plan your network design around it, which of course results in a suboptimal network design. Now your next three drivers really are related to scalability. So here you might have concerns with sustained bandwidth growth, driving the need for more fiber capacity, and then if you couple that with a high cost for the fiber, or perhaps a lack of fiber availability in a given area or application, that's really driving the need to get more capacity on each fiber. And then all of these things are combining to push the vendors to add new features and tools to the photonic line system and the ROADM node, such as automatic configuration and setup, connection validation, especially as your ROADM sites and your architectures to support more degrees. They support more add drop channels. You want to make sure that fiber connections are all correct. Bidirectional OTDR for troubleshooting, channelized ASE noise to simplify and speed up channel adds, especially as we extend the usable spectrum from C-band to C&L-band. And of course, the ability to automatically characterize that fiber network and then calibrate the line system so that it functions without impacting any of your existing wavelengths as traffic is added or rerouted at your ROADM sites. So with that, I'll go ahead and pass it over to Rob for Fujitsu's perspective.
Thanks very much, Kent. So at the beginning of this, Tim showed a number of charts that had nice smooth curves that showed the growth in traffic that was occurring across the industry. And while that is true for industry averages, I think many of us could agree that trying to predict that for any given site is a little bit more challenging, and it's much more choppy environments. I think few of us would have been able to predict the challenges that networks have occurred this year, driven by the sudden shifts in work from home, learn from home, stream from home. So the point is that as we develop and design our networks, we need to be able to adapt to changing and unpredictable challenges that we're going to encounter. And we need to do so while maintaining quality. And we'll talk a little bit more about that a bit later on. But I think a really key thing is some of the things that Tim was pointing out at the beginning, where he was showing, yes, there's going to be traffic growth, but revenue growth is not going to be increasing at the same rate as the traffic growth. And that means all of us need to be looking at innovative ways that we can reduce the overall cost per bit. And that's going to be a fundamental driver in decision-making on how we plan our line systems. And I'll turn it over for the next section.
Thanks, Rob. So in this section, we're going to look at new options and solutions. We'll look at some of the history of optical switching and then look at solutions that allow us to add capacity, increase the efficiency and the use of the spectrum, and be compatible with the evolution of coherent modems. Brian will kick this off, so I'll turn it over to Brian on Lumentum's view of new options and solutions.
Thanks, Tim. So before we delve into the solutions to these challenges that have just been raised, let's have a look at how the device technology, the ROADM device technology, has evolved. So the plot you can see on the left there basically tracks the wavelength selective switch, or WSS, port density over time. So you can see from that that it's increased by over 2 orders of magnitude since the first introduction of wave blocker technology way back in the early 2000s. And functionality has also significantly increased quite steadily over that time. And if you look at the right-hand side, you can see the blue line there is showing how the device complexity has increased. That's almost an order of magnitude in complexity increase in just the past decade. But also looking at this, you can see the time taken to manufacture these, much more complex devices has plummeted over the same period. Why? Well, that's a result of improved processes, better automation. So the point here is that there have been significant advances in the device technology and capability in recent years. So, the title of this webinar is Future-Proofing Optical Networks. So the big question is, where are we in our pursuit of a future-proof ROADM? Okay, so let's have a look at how today's ROADM technology stacks up. So the ROADM hardware and line systems, they're typically in service for a long period of time. But transceivers and transponders, they change every few years. And those future increases in interface rate, they're going to be achieved by first increasing the baud rate and then adding carriers. So, channel bandwidth is going to continue to increase. Now, as Kent mentioned before, the WSS devices used in ROADM, they're flexible grid capable. So that means that transceivers evolve to higher baud rate and wider spectrum. The channel bandwidths can be adjusted in service to support this, so that's great. We also talked about the need for C&L-band overlay where fiber scarce. And today's line and add-drop WSS hardware, they both support C&L bands, so operators are able to scale that usable spectrum and capacity. Now, I previously mentioned how the port density of the devices has improved significantly over the years, so basically squeezing more ports into a smaller footprint. So 32 port line WSSs as we have today, they easily scale to 16 degrees and leave plenty of additional ports for local CDC add-drop. So these high port count WSSs, again, they're allowing operators with lots of fiber to activate multiple fiber pairs per route, and that's principally for capacity scaling. Now, the contentionless N-by-N WSS, that's the most recent addition to the ROADM hardware toolbox. And Tim mentioned earlier that if we want to achieve lower cost per bit, then data rates and channel bandwidths need to continue to increase. Now, because it's inherently low loss, the contentionless N-by-N can achieve this without a limit in the maximum channel bandwidth. So, flexible grid, C+L band capacity, high port count devices, and contentionless WSS. I think the good news for you is that the ROADM hardware that is available today is already future-proof. So with that, I'll pass over to Kent for Sienna's perspective.
Okay, thanks. So next we're going to talk about how an integrated C&L-band approach that uses ASE noise loading can simplify your L-band expansion. So you can see here with the initial view on this slide, your initial deployment starts with an integrated C&L-band equipment at your amplifier sites that's optimized day one for both the C-band and the L-band. And you can see that in the building block diagram there on the left, where there's both a C-band and an L-band EDFA that's integrated into a single line amplifier card. And the Raman that's deployed can support both C and L-band. At the ROADM node, the card with the C-band WSS also happens to include some L-band amplifier and ASE noise generation components, but the actual L-band WSS can be deferred to reduce the initial first cost until you're actually ready to expand into the L-band. With this architecture, everything on the line's optimized and ready for L-band from day one. If we look at the wavelengths on this line system, you can see that we start with some traffic carrying wavelengths in the C-band, and then the remainder of the C-band is populated with channelized ASE noise. The L-band's filled with bulk ASE, and so the system's actually behaving as if it's fully filled across the C-band and the L-band day one. And then if we just animate that, you can see that as you expand from the C-band to the L-band and start carrying traffic on your wavelengths in the L-band, you don't need to revisit any of those amplifier sites to upgrade your EDFAs or your Raman to support L-band. We simply replace the bulk L-band ASE with channelized ASE noise, and then start substituting actual wavelength power for ASE whenever a new wavelength's added. This gives you optimal performance across the lifetime of the system, regardless of how much capacity you happen to be running across it at any given time. And by optimizing the network for C and L-band, it maximizes your fiber capacity. You get double the usable spectrum with the L-band, and you want that to mean that you get double the fiber capacity. And of course, you want to do that in a hitless way that doesn't impact any of your existing C-band wavelengths. This integrated C&L-band approach is really designed to simplify the deployment and the operation of the C and the L-band across the lifetime of your system. Now, a lot of network providers are also considering new technologies such as coherent pluggables, and they want to understand what are the impacts if they're using a ROADM-based line system. And as you can see, there are some considerations here around things like the output power for the modem, whether the ROADM's using a filtered mux-demux or a passive mux-demux. And this really gets into the details of the actual ROADM architecture that's being deployed, whether it's like a multicast switch or a more modern contentionless WSS. The vast majority of ROADMs that are deployed right now are still using that passive mux-demux filtering, and there's a performance impact that's associated with that. You also want to support a mix of signals and a mix of baud, and you need to understand what does that mean for your channel planning. And of course, the control system is going to play its part here by equalizing any of your pass-through wavelengths at a ROADM location. So at the end of the day, you kind of want to be able to achieve some level of balance between the characteristics of the modems and the devices that are adding the wavelengths to the network, and the incremental photonic modules are now being introduced to be able to accommodate for that mixed signal power disparity. Now, the exact functions that are going to be included in these new modules that are being introduced, those are going to differ depending on what you actually need to accommodate in your specific network or your specific application. And with that, I'll go ahead and pass it back over to Rob.
Thanks, Kent. So I'll just change this slide over here. So as both Brian and Kent have mentioned, L-band is going to become important, and I wholeheartedly agree. But not all sites are going to need L-band day one. It's possible that some sites won't need L-band at all, and there's an opportunity for you to save some money and keep your cost per bit of your network down. But when you are going to need L-band, it's important that you have the ability to add it seamlessly. So if you've got existing traffic on the C-band, you need a mechanism to merge that L-band traffic on without having any form of service disruption so that you can maintain the quality of the network. And to do that, you can use an integrated port for expansion for it. So looking for ROADMs that allow you to add that capacity later on in the future will be of value. But that's just one example of some of the things that you may have to encounter in the future. The lifespan of the ROADM is quite long, and you need to think about where things are going to go in the future. Now, there are some vendors that will say OTDRs are needed at all sites, for example. And there's some validity to that. If you have an OTDR everywhere, it streamlines things from an operations perspective and makes you puts you in a position to be much more responsive. But it comes at a price. And looking at different ways at how you can deploy OTDR, there's some opportunities for savings. So you may put OTDR at sites that are particularly high traffic sites, for example, so that you can be particularly responsive. But perhaps you've got a spur site out in the middle of nowhere, and it doesn't really have any high-profile traffic on it. It may be perfectly acceptable to have not deploy an OTDR out there and just have a tech go out to site. So that's one example. Now, one thing to keep in mind with if you're looking at deploying OTDRs is Many of them operate in the L-band. So if you're thinking that you may need to go to the L-band in the future, make sure you're not choosing an OTDR that also operates in the L-band. Another thing that will be coming down the pipe is forward Raman technology. Now, forward Raman technology exists today, and I wish I had more time to talk into it in greater depth. But the reality is that forward Raman has limited application and use for some reasons I won't go into at the moment. But a lot of that is changing, and the technology is improving. It's perhaps not productized yet, but it's coming down the pipe, and it will allow you to extend the reach of a given span by up to 40%. Or if you have the same span distance, you may have the opportunity to move to a higher bandwidth or speed. But again, just like the OTDR, the L-band, you need the integrated ports available inside your ROADM to add that capability seamlessly over time. And one thing that can really help you in adding chunks of functionality in a cost-effective way is by using a modular blade-based architecture. There's not one size fits all. We have different sites in the network, whether it's spur sites, ring sites, or hub sites, and those different sites have different needs. So Kent spoke a little bit at the beginning about the differences between C, CD, and CDC technology. CDC technology is fantastic. It's very flexible, and for hub sites where things are changing, you can dynamically reprogram those sites to add and drop the same wavelength at the same site. There's all kinds of wonderful things, as Kent pointed out. But do you really need all of that functionality at the spur site? The directionless capability is kind of pointless if it only goes one direction. So I think the point of having a modular blade-based architecture, it allows you to deploy and pay for only what you need when you need it. You don't over-engineer your network on the day one, but you have the opportunity and the flexibility to add different components and capabilities as you go on. And that's done through a combination of integrated ports, in-service upgrades, having a common software across everything, and of course, backed by trusted support. And with a combination of those capabilities, then you're ready to really future-proof your ROADM network. And now I'll turn it back over to you, Tim.
Tim, are you on mute?
Yes, sorry. Thanks for a reminder. Yeah, in this section, deployment applications will cover applications where increasing capacity and adding ROADMs, ROADM capabilities being used to future-proof networks of various types. Kent will start us off with a deployment application that's Sienna Seed, where they're adding C&L and ROADM capabilities. So I'll turn it over to Kent now.
Okay, thank you. So you've already seen some material and heard some things around L-band earlier in the presentation and how the ROADM and the line system can support it to expand the usable spectrum to ultimately carry more capacity. From an RFP perspective, we're really starting to see more and more network providers are starting to ask about, how can I increase my usable spectrum? What are the options for things like L-band? And how is that going to affect the deployment and the operation of my network? And this slide just gives an example of one such network operator. So this is Telia Carrier, who wanted to expand its U.S. footprint to deliver more bandwidth for its customers while being able to reduce deployment and operational costs. So Telia chose to deploy an integrated C&L-band solution to expand into the L-band, double the usable signal spectrum, but do so in a way that doesn't impact any existing C-band channels. So this gets back to what was discussed earlier, where an integrated C&L-band approach can optimize the network for both the C-band and the L-band day one to simplify your expansion into the L-band, do it in a stable, hitless way, and operationalize it in a way that reduces your costs and eliminates things like amplifier site visits to upgrade to the L-band. And with that, I'll go ahead and pass it back again to Rob for Fujitsu's view on applications and deployments.
Thanks so much, Kent. At Fujitsu, we're doing things a little bit differently. We've spoken a little bit earlier about having 3 different types of sites: spur sites, ring sites, hub sites. And I've shown on this ring here a mix and match of different combinations so that you can really right-size what's needed for that particular site in order to keep your costs down. So we've already spoken about CDC and OTDR capabilities, but we also could talk a little bit about the number of degrees. Again, some vendors want you to deploy everything day one, all the bells and whistles for maximum flexibility, maximum number of degrees. And again, that's going to come at a cost. I mean, we've all seen this movie before, and we all know how it ends. People may have clever pricing mechanisms where you only pay for what you need when you need it, but at the end of the day, there's a bean counter somewhere who's figured out how the vendor is going to get their money back over the long haul, whether it's activation fees, license fees, port charges, whatever. We're trying to do something a little bit different, where we're trying to only deploy what you need when you need it so that we can keep our costs down and pass along genuine savings to the operator. So, for example, in this site, we can show the different number of degrees that you might have at different nodes. About 80% of the nodes of the sites in a network are usually 1 or 2 degree sites. And so we took a look at 1 and 2 degree nodes, about 1,000 of them, and followed them over a 7-year period. Less than 1% of those nodes ever grew to be over 4 degrees. And so we developed a rather unique add-drop blade that uses entirely passive components for 4 degree sites. So there's an opportunity, again, for you to save that cost per bit and right-size your network by only deploying what you need. Now, I'll walk through a couple of examples on here. Obviously, you can add ports. That's a simple thing to do, and you can expand your network easily with that. You could add OTDR as we talked about earlier. Perhaps the site starts adding more traffic, and you decide that you need it. Or perhaps the landlord has changed, and site access is becoming more difficult, so it's no longer reliable to be able to send a tech to site with an OTDR when something goes wrong. Maybe you need to add it. Having those integrated ports that allows you to add that capability when you need it is of value. Similarly, you can look at a site that perhaps wasn't very important at the beginning and perhaps only had colorless capability with a small number of ports, but suddenly you've added a new ring to it, and suddenly you decide that you want CDC capability. Again, a modular architecture enables you to add those components needed so that you have that flexibility. We spoke a lot today about adding L-band. Now here, I should have shown it as a ring rather than just connecting a few sites, but you get the idea that you, again, have the ability to add different components, different modules to sites to add the traffic only where you need it. And then finally, as we talked about earlier, the forward Raman capability. So, for example, if you've got a regional link that you're adding and you want to add forward Raman capability to a site, you've got the expansion ports to be able to adapt it so that you future-proof your ROADM network. And I think the main message with all of this is that having that modular blade-based architecture really allows you to right-size your network so that you don't over-engineer, you don't pay for stuff that you don't need, but you have the flexibility to grow and expand as you need it. And I think with that, we'll turn it over to Tim to walk through some Q&A. Tim, are you on mute there still?
Yeah,
actually, yeah, thanks, Rob. Kent and Rob have focused on how these new systems and capabilities are being deployed, and I'd like to just quickly have a look at what might come next. So, as part of the market trends, Tim mentioned that the Capex is projected to grow at basically single figures, while the capacity is up around 30%, and that the higher data rate coherent transceivers, they're really needed to keep pushing the cost per bit lower. So currently, where there's lots of fiber and there's multiple fiber pairs per route are being used to grow capacity, each additional fiber pair added needs a separate ROADM degree, so the cost scale linearly with the degree count. What we would like is a way to reduce the cost per unit bandwidth, or said another way, reduce the cost per deployed degree. So today, one twin WSS serves a single degree, that's shown on the left. In the future, we'd like to, be able to enable a more cost-effective and compact scaling by, integrating more WSSs into a single device. So, for example, like a single device with 4 WSSs, that would be a quad, that could serve 2 degrees over the same fiber conduit and still be fully compatible with the twin devices that were deployed earlier. Similarly, we know that deployment of both C&L bands is important, as Rob and Kent have both said previously, and that might be just because fiber resources are constrained or where the cost is prohibitive. Now, we can do this today, as shown on the left, and that's essentially a separate device for C and a separate device for L-band. In this case, again, the cost scale is linearly with capacity. So, integration of C and L functions, that can provide a future path to reducing the cost per unit bandwidth, as well as simplifying the interconnect between WSSs. In fact, you've just heard Kent talking about how we're already seeing integration of C and L band functions today to help simplify deployment. So moving on, let's move on and take a look at the sponsor approaches, and I'll start us off there. I talked earlier about the essential elements of a future-proof ROADM, including flexible grid capability, the support for both C and L bands, high port count WSSs, and contentionless M/N. So the key hardware elements that enable this are available today in mass production, and are already being deployed in next generation networks, so that's a good thing. Now, in the past, when we had lower port count WSSs, there was always a trade-off between how many degrees you support and how many local add drops you could achieve. But with a twin 1x32 WSS, that solves the problem. It allows for larger ROADM nodes with more fiber pairs per route, and that means you can basically scale the usable spectrum, but it still leaves plenty of ports for those local add drop. And the contentionless M/N, that's essentially another important piece of the puzzle. On the one hand, it allows you to continue to evolve coherent transmission to higher rates and higher channel bandwidth, but the flexible grid filtering in that WSS means that out-of-band noise can be eliminated. So the system performance is improved too. And what that means is we can take full advantage of today's advanced multi-hall transceivers to achieve the best spectral efficiency times reach. So with that, I'm going to pass over to Kent for Sienna's perspective.
Okay, thank you. So we've seen and we've heard several different considerations and drivers around flexibility, capacity, density, intelligence, and Sienna's answer to these requirements is the 6500 RLS. It's an ultra-dense, modular, flexible photonic line system that adds embedded instrumentation to improve automation, intelligence, and operation of the network. A next-gen ROADM system really isn't just about the WSS and being able to configure it to support different configurations up to and including things like contentionless. It's really about having a next-gen photonic line system, not just the ROADM, but the entire thing, that supports the right configurations and brings more intelligence to the table to simplify the operation of the network. The RLS integrates the ability to characterize the fiber in terms of length, loss, latency, dispersion, and even nonlinear characterization. It provides connection validation, so you can be sure when your technician leaves the site that it's fibered correctly and you don't run into issues down the road. That's especially important as you start to scale to these higher degree ROADMs and more like CDC type architectures where you have a lot of different fiber connections. It's got bidirectional OTDR, which can be used to pinpoint fiber issues, to deploy technicians to the field faster and more accurately. The RLS brings together that integrated C&L-band approach for hitless, predictable expansion to the L-band for increased fiber capacity. It supports a range of ROADM and point-to-point configurations, and its different shelf sizes pair well with the compact, modular transponder systems that are prevalent today, such as Sienna's Wave Server family. And it's built to be a modern and programmable infrastructure with open APIs, model-driven configuration, and streaming telemetry. So with that, I'll go ahead and hand it back over to Rob again.
Thanks, Kent. So here at Fujitsu, we've got, rather than one unit, we've got sort of a portfolio of capabilities that, while physically separate, can be logically aggregated through software. So with this compact modular blade design, we can right-size the network for the different types of sites, whether they're spurs, rings, or hubs. So, for example, with the add-drop capabilities of a spur or ring site, we've got a passive solution that has no active components that can be used for up to 4-degree sites, and that can be used to keep the cost of those vast number of smaller sites down. We also have the large WSS-based add-drop capabilities so that you can grow up to 8 degrees. Similarly, we have different options for C, CD, CDC capabilities so that we choose the right technology for the site. Of course, everything is very cost-effective and scalable, where you're not having to pay for things or deploy things up front, and you just pay as you grow by really just adding the components that you need as you need them. Finally, we, of course, offer our own Virtuora SDN control and orchestration software that integrates everything together and controls everything seamlessly. But all of our nodes are also have open APIs so that they can be integrated into other third-party platforms if that is a need that an operator may have. So again, the main point here is not just one system that's one size fits all. It's a portfolio of capabilities that allows you to right-size the network so that you only pay for what you need when you need it and avoid over-engineering. And I was a bit premature earlier. I guess now it's time to turn it over to Tim.
Thanks, Rob. Yeah, and I want to thank the audience for viewing the webinar today, and also thank our sponsors, Ciena, Fujitsu, and Lumentum. I will go through some conclusions, and then we will open it up to questions from the audience. If you have any questions, please submit them in the Q&A tab, using the Q&A tab. Okay, so back to the revenue and Capex. This is showing what's going on with revenue growth and Capex growth. And as you can see, really driving the way in both of these is the ICPs. The CMPs are also showing some growth, albeit from a pretty low base, relatively speaking. We expect there will be mild growth with fixed and mobile CSPs, but really maintaining this kind of flat thing and dwarfed by the deployed bandwidth growth. So this will continue to put pressure on equipment manufacturers to decrease the cost per bit. And really holding the capital intensity or the Capex over revenue in line. The industry vectors for future-proofing optical networks are really get the most out of the deployed fiber. Fiber is very expensive. As we've approached the Shannon limit, and Brian showed earlier, we're not really able to increase more capacity in the C-band, only incrementally. We're 1.5 dB away from the Shannon limit, so there's not a lot more we can get out of it. So we really need to increase the amplified spectrum by including C plus L. And we need, for both increasing capacity, it's important to go to higher speed modems, but also decreasing the cost per bit. This has been a vector we've been on for since the beginning of optical networks, and it will continue. Another area there is moving to more application-specific modems. As Kent had outlined, there's a move to going, especially for like DCI applications, having a modem that's designed to do these point-to-point 80, 100-kilometer links. And we should see more and more of that kind of specialization as well. The other thing is space division multiplexing, or essentially using more fiber. When you run out of capacity on the high capacity nodes, lighting up more fiber is sometimes the only option that you have. But other areas to help decrease cost per bit is, flexible add drop and with pay as you grow, as Rob has mentioned. So, only paying for what you need as you need it and growing that way. But all of these really require a seamless upgrade. You can't be shutting down traffic to add L-band or to add other channels. So these are some of the vectors the industry is on and some of the main vectors. Looking at coherent modem forecasts, we continue to evolve to higher rates. By 2023, we expect 400 gig plus, so 400 gig, 600 gig, 800 gig will supply over 50% of the deployed bandwidth in 2023. ICPs, we expect that their capital intensity will grow from about 7% to about 8.5%. And the service providers will stay around 18% where they've been with capital intensity for quite some time. And so this is split up by the maximum, we segment the market by the maximum capability of a given modem with multi-rate modems. The maximum would be 800, but it may be used at 400 with longer reach. But that's how that's segmented. So this is our forecast for optical switching elements used in ROADMs, so essentially wavelength selective switches. We expect that the 1x(n) will dominate over the forecast period. And ROADMs or wavelength selective switches of various types will reach over $900 million by 2021. We expect the newest that Brian had alluded to, the M/N WSS modules, to grow quickly, albeit from a somewhat small base, but we're expecting over the period of 2020 to 2024 a 90% compounding annual growth rate for wavelengths, M/N wavelength selective switches. Okay, so that concludes the webinar. We will now turn it over to Q&A from the audience. I think we have about 5 minutes to get through some questions. So let me start out with a question concerning degrees of ROADM. The question is, has there been a need for high 10+ ROADM nodes, especially with the increase in data center interconnects? And has this become more prevalent recently? What is driving the need for the degrees for the most popular ROADM architectures? Brian, do you want to field that one?
Sure. So if you think about, typical ROADM nodes today, they only serve a maximum of 5 to 6 physical directions. And I don't think that's really expected to change. But the capacity is growing, like you said, Tim. So we need to add more usable bandwidth. So in lots of cases, that means adding more fiber pairs per physical direction. So to me, it's capacity growth that's driving the need for more degrees, and not the increase in the number of physical locations that need to be connected. And in fact, we're already seeing this type of strategy being deployed today in different geographical areas. And yes, we are seeing a need for 8, 9+ degree counts for that reason, but it's for capacity expansion.
Thanks, Brian. So kind of along these lines is another question. Typically DCI links are point-to-point and pretty simple optical networks. The question is, and Kent, probably if you could field this one, is there a value for ROADMs in DCI networks?
Yeah, sure. So yeah, for metro networks, some service provider networks, obviously they have a large number of sites. They're going to require greater degrees of connectivity where ROADM can provide a clear benefit. But for your simplest DCI point-to-point architectures, is there a value for ROADM in those networks too? I think in a point-to-point application, a fixed filter add drop might be just fine. ROADM may not be required. Fixed filter architectures are easy to plan and deploy. but they're fixed to a specific channel width. And depending on the filter you're using, you may not be able to leverage new coherent technologies and their economic benefits. So as you want to move to more flexibility, you can add ROADM for colorless capability, which still is going to retain the simplicity of a point-to-point architecture for a DCI network, but now it introduces flexible grid to future-proof to allow you to support those new higher baud signals. And then if you want, you can move your flexibility all the way up to a full CDC ROADM to enable wide-scale cookie-cutter type deployments, which is really becoming more and more important as you move to these larger scale deployments. There are considerations on cost, obviously, as you introduce that flexibility to the ROADM node, but ultimately it's about striking a balance between your traffic requirements and the flexibility and reconfigurability that you prefer. Depending on the operator, we're definitely starting to see interest in ROADM for DCI point-to-point type applications, but of course there are still fixed filter configurations that are applicable here too.
Thanks, Kent. Okay, this next question, Rob, you had gone into a lot of detail about the modularity of, or modular solutions in Fujitsu, and we have a question. With these modular or blade-based architectures, do I have to have an electrical tech go to each site every time I want to add a blade or a module?
Excellent question. The answer is no. There's options to have housing units so that you can have space and reserved and power pre-wired to add extra blades. If you don't want a housing unit, you can also just have the rack pre-wired for expansion in advance, so you don't need to send an electrician out there. But it's also worth remembering that if you're in like a leased facility, you may be paying per fuse position, and if you may want the flexibility of not pre-wiring something so that you can save some money on those operational expenses of power. So I think the point is again giving as many flexible options as possible to the operator so that they can choose the solution that's right for their specific site.
Okay, thanks, Rob. I think we have time for probably one more question. So let's, for applications that do not need directionless feature and require a low number of waves to drop, would transponders be able to connect directly to unused twin WSS ports without using filters or multicast switches? I don't know, Rob or Kent, do you want to field that one?
Yeah, I mean, I can talk to that. So we actually have a name for that. We call that colorless direct attach, and yes, you definitely can connect your transponders directly to the ROADM.
Okay, thanks, Kent. Yeah, we've reached the top of the hour, so I want to thank all the participants and our sponsors, Ciena, Fujitsu, and Lumentum again, and hope everybody has a good rest of your day. Thank you a lot for your participation. With that, we'll close the webinar.
Thank you, Tim, and I'll thank you as well for leading our discussion today, and also once again, thanks Kent, Rob, and Brian for this very detailed and informative discussion. So again, thank you for joining us, and have a great rest of your day.